Okay, thank you. So we'll continue with the concept of dynamic partitioning, right, that we were discussing earlier. Let me just share these slides. Okay, so before we start, we have seen two types of fragmentation yesterday. One of the fragmentation is known as internal fragmentation, right? And why is it called internal? What is the reason for that? When you divide your memory into a number of partitions, what signifies or what is meant by internal fragmentation? It is the wastage, or you can say it is the wastage that occurs within partition or outside the partition. It is within the partition, right? Remaining space inside the partition, okay? While if you have the method like dynamic partitioning, you will continuously be doing swap in, swap out, right? Because many processes execute during a period of time, and due to that, small amount of holes are getting created, right? And there will be number of holes, okay? And due to that, you are going to have such a scenario where there will be very small size available spaces, right, at various locations, right? And this wastage of memory is actually outside any of the partition, and that is why it is known as external fragmentation. So which one is more dangerous, internal or external? Or it depends upon the allocation. What do you say? Which one is more costly, in other words? Okay, internal, external. Fine, we'll analyze that, right, later on when we'll compare the methods, right? See, internal fragmentation will not be costly if the size of partition is small. Yes or no? If the size of partition is small, internal fragmentation will not be costly. Okay, because if the partition itself is of small size, the amount of fragmentation is going to be smaller, right? And that is the reason for which we use paging, right? Paging uses this concept, right? Instead of going with a large scale or average scale partitioning, we divide with small, we go with small scale partitioning, right? And that reduces the amount of internal fragmentation, right? And when external fragmentation is not a concern, in which scenario external fragmentation will not be a concern? Where the amount of external fragmentation is minimum. Can I say that? Right? If your amount of external fragmentation is, let us say, just 1 MB or 500 bytes, right? Although it is occurring at various intervals, that is fine. Because if you sum everything up, right, it won't cross more than, let us say, 4 MB or 5 MB. Then it is tolerable, right? So basically every method has its own limitation and strengths, right? Fixed partitioning versus dynamic partitioning. This is the difference. If you are asked this difference, you should be able to define both the terms first. That is the first point of difference. And the second point of difference is, in one method, we are having the problem of internal partitioning, or sorry, internal fragmentation. And in the other case, you are going to have problem of external fragmentation, right? Okay. Now, yesterday we discussed about defragmentation, right? Generally in Windows, we have that kind of capacity, right? That is called compaction in OS, right? Compaction is nothing but bring all the empty pieces together, right? Bring all the empty pieces together. And generally, what we try to do is, we will bring all these three pieces, right, at the end, right? So that we can have a larger block over here, right? You can have a larger empty block over here. That kind of method we have to use. Okay. Now the question is, at what frequency? Yes, I'm going to come to that point. At what frequency we have to carry out compaction? If you do it very frequently, then is it a good approach? Obviously not, right? Because you are not waiting. We have to wait for some time. Let the system run for some time, right? Yes, that is one of the option, right? You analyze the past behavior of multiple types of processes and see what is the average time, right? After which you should carry out the compaction task, right? So your Windows, if it is doing it automatically, it is having some method and some logic, right? So it might be predicting based on the past performance, right? As you know, Windows has kept everything proprietary, right? So you need to search, right, which kind of approach they are using. You might get some answer from somewhere, right? So are you clear with what is compaction? Right? Compaction is required, right? That is the summary, but the frequency of compaction is a question, right? Okay. So what is compaction? As I said, OS will move processes so that they are contiguous, right? We will shift the processes. So this process P4 will be moved over here in this location. Process P3 will be shifted over here, right? So that at the end, you have the empty space. That is how the compaction method works, right? You can say that, yes, CCleaner is doing a similar task, right? But for that, you need to give OS privileges, right? The permissions are required. I think you are asked that, right? When you are installing CCleaner, you are giving the permissions that can perform the compaction, right? So if you allow, then it can do, right? Definitely, yes, exactly. You require admin rights. Fine. Now, the next point regarding compaction is it requires dynamic relocation. What is dynamic relocation? First of all, what is relocation? We had loaded the process in some fixed location earlier. Now you are shifting that process upward. That means the addresses will change. Yes or no? Addresses will change. And when this is going to happen? At runtime. Right? Because compaction is a runtime process, basically. Right? And that is why it is called dynamic relocation. Fine. It is happening at runtime, right? As well as you are shifting the process. Shifting the process means relocation. It is happening at runtime. That means it is dynamic. Okay. Clear with this term? What is dynamic relocation? And definitely, dynamic relocation is a costly affair, right? Because you are shifting a process from one location to the other. Now, you need to take care that addresses are handled properly or managed properly. Otherwise, what if you overwrite some of the existing process, right? That process will not be able to execute now onward, right? So a lot of care has to be taken when you are performing this dynamic relocation, okay? In summary, what we can say is compaction is a time-consuming task, obviously, right? And it wastes very important CPU time, okay? So rather than that, if you want to avoid compaction, right, what is the option? Try to reduce the amount of fragmentation. Yes or no? If you want to avoid compaction, make sure that your wasted space is minimum so that we can ignore it ultimately. Fine. So for that, we have the concept of paging and segmentation. We'll see that later. Fine. Once we are done with this. So as compaction is costly, the other option is OS can make intelligent decision when a process is brought in, right? So basically, you think about the placement of the process. You place the process in such a way that you are occupying the best partition, right? And best partition means what in general? You fit the process into such an area where minimum wastage is occurring. At least we can say minimum, right? No wastage is an ideal scenario, right? That you are not going to have in a practical situation, but at least you can reduce, right? So if you want to achieve this, search time is going to increase. Yes or no? If you think in terms of algorithms, you have to search for the minimum amount of space which is available where you can fit this process. Are you getting the approach? Right? You need to find out minimum amount of space where this can be loaded or process can be loaded. So for that, we have three algorithms. Now again, you can understand from the name itself. The first is best fit. So what should be the strategy of best fit? Yes. Find out the best suitable hole. That means it is wasting minimum memory. It is wasting minimum memory, right? Yes, you have to search. That is a drawback. We'll see this in detail, right? Now, what is next fit? What do you understand by this term, next? Suppose your memory pointer is pointing to some location at this point, right? So we don't want to search the entire memory. What this method says, start from the current position and search for the next available block. Start from the current position and search for the next available block. Are you getting the strategy? Right? Next to current, that's correct, Janil. Right? Yes. Okay, good. Next comes first fit, simplest strategy with minimum cost. Right? So if we assume that our pointer is at beginning, right? Then what is the strategy we can follow? Find out the first hole wherever it is, right? But there is a major issue with this, right? What if the first available space is very huge and your process size is very small? Then a lot of wastage will occur. Are you getting? Right? So every method again has its pros and cons, and that is what we are supposed to analyze, right? So no method is perfect, fine. But depending upon the situation, you can choose the algorithm. You need to be dynamic in this approach, okay? Let us analyze these algorithms in detail. Best fit is known as best, but it is called worst performer, right? So there is a contradiction over here. Why? We'll see that, right? First, let us see the strategy. What do we do is we choose the block that is closest in size to the request, okay? Suppose your request is 2 MB, right? And you are having a 3 MB block, as well as you are having a 5 MB block, right? So which block you will be selecting? 3 MB one, because over there the wastage will be 1 MB only, fine? But why it is worst, right? Because you can see the reason. Since smallest block is found for the process, we are left with smallest amount of fragmentation. Do you agree with this? Right? So you will litter your memory with very small holes, right? Which will be totally unusable, right? And what if this kind of system executes for, let us say, half an hour or 1 hour, right? Your memory will be filled with non-usable space, right? Very small space, right? And due to that, yes, and due to that, what is going to happen? Compaction will be required more frequently. Do you agree with this? Right? As you are having very small holes, we can't tolerate that, right? Because if I merge all the small holes together, I can create, let us say, a 15 MB of space, right? So compaction is required very frequently in this case, and that is why we say that best fit is the worst fit actually, or worst performer, okay? Yes, more small holes will end up wastage of huge space. So that is why if you want to avoid wastage, what is the only option? Compaction. And compaction is not an easy job, right? It requires CPU time, which we can't share. Okay. So this is about best fit. Clear with this first approach? What is the approach and what is the disadvantage, right? Okay. What is the advantage? We have not discussed that yet. Right? What is the advantage? It's very easy to find out, right? If you convert the disadvantage into the positive sense, the advantage is what? It is minimum internal fragmentation. Yes, we can say that, right? But over the period of time, this advantage becomes disadvantage. Are you following this? Right? Over a period of time, the advantage becomes disadvantage, right? Okay, good. Let us go for first fit now. In first fit, we scan the memory from beginning. As I said, we assume that the pointer always returns to the beginning, right? When we are searching. So you choose the block which is first available, right? And it is large enough. there are two conditions we need to satisfy. First is you need to look at the size of available space. If the size is sufficient, and the second condition is it is the first available block. Okay. If both the conditions are satisfied, you can go with first fit approach. Okay. Obviously, this is the fastest approach because you are assuming again that you are starting from beginning, right? And you will allocate the first block that is available. As well as, is this a simple approach? Can I say? If you want to write the algorithm for this, the program will be very simple, right? Just look for the first available block. That's it, and allocate it. Fine. Now, what is the problem? Let us look at that. It may have many processes, actually processes over here, I'll change that, loaded in the front end. Many processes loaded in the front end that must be searched over when we are trying to find a free block. For example, yes, small processes can be allocated to larger spaces. So amount of fragmentation will be more. Agreed, Urjit. That's correct, right? Okay. But right now we are discussing a different point, that is many processes. Suppose you are running first fit for some time, right? Let us say for half an hour. Now, what is the probability that you will get your first fit block very soon? You will have to search for a longer period of time or not? I'll repeat. If you are running this algorithm for half an hour or 1 hour, right? And this strategy says that you are occupying the first available block, right? Now the first available block will keep on shifting downward, right? So as you go along over the time, right, the searching time will increase. Are you able to understand this point? Right? So over the period of time, this actually becomes a bad performer, right? And another problem is you will have small holes in the front, right? If the space is allocated in such a way, right? So you will require to do compaction in the upper part mostly, yes or no? Because we are allocating the memory from the beginning, the compaction will be required in the upper part only. Agreed? Right? Still, if you compare first fit with best fit, which is a better option? As far as the amount of compaction required, if you consider that as a parameter, then which is the better approach? First fit or best fit? The last point, I think, gives you the difference, right? Yes, so what is the answer? Definitely first fit you should go with, right? Because the compaction is still required, but just in the upper part, okay? It is possible that you might not have to compact the entire memory, right? Okay. Now, next is next fit, okay? So the strategy is again simple. You remember the last allocation. You remember the last allocation and start scanning. Yes, it may be carried out on toward lower part as well as, yes. So if you continue the first fit for a long time, then definitely it becomes near to best fit in terms of compaction. Agreed, right? That's correct. Okay. But usually when you are employing first fit, the compaction is carried out more frequently so that we can make the later space free, right? Best fit is never used, obviously, right? So you have only two options. Either you go with first fit or next fit, depending upon the type of process or type of available memory. You need to go with either one of them, right? Best fit is just used for comparison purpose, right? Okay. So in next fit, you scan the memory from location of last placement, where you placed at the last, where you allocated the block at last. From there you start scanning. Okay. Now it is highly probable that you might be in the middle, isn't it? After the execution for some time, you might be in the middle, right? So where the block will be allocated? Towards the end. Yes or no? Where the next block will be allocated? Towards the end, right? This creates a major problem. Why so? Because when you are allocating the block towards the end, right, generally the end part of the memory is having larger availability. Yes or no? end part of the memory is having larger availability. So if you continue doing this, right, you are actually breaking down the larger available block into smaller parts. Now, after some time of execution, if you are getting a request for a, let us say, large amount of block, will you be able to find that using next fit? After over the period of time you execute this algorithm, right, the request comes for a large block, right, that won't be accommodated, right? It will ignore repeating search of memory. Yes, definitely. So there is an advantage also, Urjit, right? But right now I'm discussing the problem first, right? Yes, if it reaches the end, you need to circle, right? Start from beginning, right? You need to consider the memory as circular, fine? Or else what you can do is do compaction, right? And then continue. There are two approaches. Getting it, Janil? Okay. So the strategy that we use in next fit more often allocates a block at the end of the memory where the largest block is found. So over the period of time, the largest block of memory is broken up into smaller blocks, as I said, right? And due to that, you will not be able to accommodate a larger request unless you do compaction. Agreed? After a period of time, if you are getting a larger request, without compaction, you can't accommodate that. Okay? So, compaction is required to obtain a large block at the end. Okay. Now, if you just compare the amount of compaction between first fit and next fit, what do you say? Where amount of compaction will be more? First fit, next fit. Remember, first fit is littering your memory with small holes at front, right? You still have larger block available at the end. But in next fit, what is happening? In next fit, we are actually we are actually going to move downward, right? So in that case, we can say that next fit might require more, isn't it? Yes. Are you getting the idea? I'll repeat once again. In case of next fit, you are breaking down the larger larger memory area very quickly, right? So due to that, what is going to happen? The larger area is broken, right? So whenever you require a larger process to be loaded, without compaction, it cannot be loaded, right? So that is the reasoning behind what I'm saying is next fit might require more amount of compaction. But again, that depends upon what type of request. That is the criteria. Are you following? So those who have written first fit, they're also correct, right? Because it depends upon type of request that you are getting. If you continuously get larger process request, then which is the best approach? Think about that. If you continuously get large size block request, in that case, large size block can be found only in the next fit. Only in the next fit. Yash and Vidur, are you getting the idea? Okay, it is continuous, so wastage is minimum, so compaction should be minimum. So in ideal scenario, Priyank, your answer is correct, but we can't expect the ideal scenario every time, right? What if you are having mixed of requests, right? Small and large, small and large. Then in that case, both the algorithm might be behaving in a similar way. Are you getting the idea? Right? If your requests are like this, small, medium, large, small, medium, large, then both might be working in the same way. Okay? So it all depends upon what? Type of request or size of request, if I be precise. Yes, surely, yes, I can repeat. Next fit. In case of next fit, we start from current location. Suppose you are at the middle, right? And you start searching for the next available block. Okay. So what is the probability that which block you will get? You will get the larger block because generally the available space will be at the end when we are following next fit. Are you getting this? Yes. Available space will be at the end, right? So that is why next fit will not be wasting the memory at beginning mostly, but it will be actually dividing the available block that is at the end. Okay. Okay. In mixed processes also there, that is minimum because the circular search. So second time it may get space. Yes. But if we go with circular, then only, isn't it, Urjit? If circular is not used, then we have to do compaction. Yes or no? Yes, yes, I think that also answers your question. If you are at the end of memory, then one of the option is you can do compaction and have a block at the end, which is of having sufficient size. Are you getting? Or you can start from beginning. But actually, if you start from beginning, it actually becomes which kind of algorithm? If you again roll back, it becomes first fit, isn't it? Are you getting? Yes? Yes. So I think now you are in a position to compare the approaches, right? We can look at the example now. Okay. We have seen the approach. It is time to look at the example. Okay, good. This is the current, you can say, allocation you are given. Which approach is efficient, compaction or circular search? Ideally, you will go with compaction, Urjit, because if you go with circular search, you are actually making your algorithm first fit. So I would say you should go with compaction. Right? Yes? Okay. So now if you see the image, you are given two types of blocks. One is gray part that is allocated and the other is free block, right? That is white. Okay. And we are also maintaining last allocated block pointer, right? That is over here. You can see this, right? This is the last allocated block. This is a real scenario, right? Before image. Okay. And which approach is faster? Compaction or circular search? If you go with compaction, right, then it is not going to violate the algorithm. So I would say that we should stick to that, right? We should not try to compare the speed because we are violating the algorithm in any case. So we should not do that, right? But as a researcher in OS, right, you can think of that as an option, right? Okay. Let us continue. Suppose you are having 16 megabyte of request, 16 MB, right? So where the first fit will be allocating the space? 16 MB is your request. And the question is first fit. Give me the block space where you will allocate. 22 MB, that's correct, right? Because you are at beginning, right? Your pointer is at over here. You start scanning. Can 8 MB be fit? No. Can 12 MB sufficient? Be sufficient? No. 22, that is the only option, right? Yes, we are having internal fragmentation over here of sufficiently large size. Still, we have to go with it because this is first fit, okay? So this is the first one. Next fit. You will start searching from here, right? So in case of next fit, what is the block that you will allocate? We are not going to do circular, right? We are not going to do circular, as I said. So it is 36. And as per the method, we have just said in the method, the largest block will be split ideally. And is it proved over here? We are going to allocate this block, right? So this is actually a problem because if you are splitting a larger block, right? Later on, if you are getting a larger request, you have to do compaction, no option. So in exam, if you're asked a question, don't do circular search. Okay, I hope you are clear with that, right? All of you. Just go till the end, right? And allocate the largest block that is available. Okay. Circular search is again a research topic. We can explore later. But right now, what next fit says, keep on scanning till the end. If you cannot find a block, then what we need to do? If you cannot find a sufficiently large block, what you need to do? Compaction. Exactly. No other option. Okay. So in exam, if you are facing a case where you cannot allocate, you just need to answer that this cannot be accommodated without compaction. Right? You can mention that as your answer. Okay. Don't go in circular manner. Again, I'm repeating. Okay. What about best fit? 16 MB. Obviously 18, right? But the cost is high over here. Actually, I don't have that in this slide currently, but I'll definitely share, right, after preparing that. Right now, we don't have in this slide. Okay, so basically, 18 MB is going to be allocated. So the amount of wastage is 2 MB. Very good as far as the algorithm is concerned. But if you look at the search, right, you have to search all the blocks, isn't it? You need to find out this 8 MB, 12 MB, 22, 18, 8, 6, 14, 36, right? All of them, and find out the best one, right? So searching is a costly operation, right? As well as what will happen over the period of time? You will get many small holes, right, where you cannot fit a process. So compaction is going to be required. Okay, so this is the answer. Best fit is fitting over here. You can see this is only 2 MB, very small hole, right? First fit giving you 6 MB internal external fragmentation, but that is still fine, right? Okay. In this case, next fit is giving you 20 MB of free space. So this seems good, but we are having a major disadvantage. What if my next request is of 24 MB? Can you accommodate that in next fit? Obviously not, right? So the only way to achieve that is I need to do compaction, right? So compaction is required for the entire memory, actually. So what you will have to do? This allocation will be moved over here, right? This allocation will be moved over here, right? This will be moved over here. All the holes will be plugged, right? So that at the end, you will get the free space. So if you do the compaction in this case, can you calculate the summation of available space? 20 plus 14 plus 6 plus 8 plus 2 plus 6 plus 12 and plus 8, right? That will be the amount of space we'll get. Yes or no? Are you following? Right? So yes, whatever is the total, right? That count is going to give you the bigger space. Fine. So if you do that in case of next fit, let us say if I'm doing compaction, then for some time, I assume that I'm going to have larger space available, isn't it? 76 MB is a large space, right? And I can run my system for some time, right? So in this sense, next fit seems a good approach, isn't it? After doing one level of compaction, you are getting a huge space, right? But provided, what is your current allocation, right? That matters, right? Okay. So actually, there is no cross comparison possible of the algorithms. It depends upon the types of requests that you are going to have, right? Okay. Next comes replacement algorithms, right? This is actually a topic of chapter number 8, but we'll just go through the basics, right? In case of dynamic partitioning, just focus on the statement written over here. When all processes in main memory are blocked and there is insufficient memory, even after compaction, right? Even after you do compaction, suppose you are left with, let us say, 22 MB after compaction, right? And your request is of 24 MB, right? So what is the only option we are left with? If your space is less than, right, or if your request is less than available space, swapping is the only option. Although swapping is a costly operation because you have to issue a disk IO, you have to move your process out, right, and bring the other process in. But over here, one important algorithm takes place that is called replacement. Because which process you will swap out? That is again a question, isn't it? Right? Which process you select for replacement? Right? So we are having a number of approaches for this. We will see that in the chapter number 8 later on, right? After we are done with the paging and segmentation, because that is required for discussing the replacement algorithms, right? Okay, so just pause for some time or wait for some time, right? Okay, let us compare. We are going to move to paging next, but before that, we'll compare the approaches which we have seen, okay? This is an important slide. if you want to prepare for the exams like GATE or the exams that we are having, just you can keep this slide in your mind, right? This is going to give you basic idea, right? Fixed partitioning. The problem is internal fragmentation, right? What is the other problem? It limits the number of active processes because we are fixing the number of partitions. That means if you are having 10 partitions, maximum you can load 10 processes. Yes or no? If the number of partitions are 10, you can only have 10 processes at present. Okay. What about dynamic partitioning? If you want to overcome this disadvantages, you can choose dynamic partitioning. But over there, we are wasting the space outside the partition, right? And if you want to manage that, you can say space wastage, you need to go with either of these three algorithms, right? Either you go with best fit, next fit, or first fit. Okay, that is the approach to manage the external fragmentation. Fine. So compaction is required, or you have to go with either best fit, first fit, or next fit. Right? In either of the case, overhead is there, right? So another system was proposed by some of the researchers, and that is known as a buddy system, right? This was a simple approach because it is a tree-based approach. And as you know, tree is a best data structure in terms of traversal, search, and all other operations, right? So instead of having linear allocation, we can have the allocation in form of a tree, right? And that is known as a buddy system. Fine, so that we are going to look at with an example, okay, before we go into paging. So are you clear up to fixed and dynamic and the comparison, right? Just remember this slide, this covers everything, right? What is the concept? Okay, now let us look at the algorithm of buddy system, then we'll start with the example. In buddy system, we treat the entire available space as a single block, right, of 2 raised to u, right? The size is in multiples of 2, that's what we assume, right? If the request of size s is made, I'm again repeating, if the request of size s is made, you need to satisfy this condition, that is 2 raised to u minus 1 less than s less than or equal to 2 raised to u. For example, if your available space is 512 bytes, okay, and if the request is 260 bytes, is this condition satisfied? 260. Total available space 512. 2 raised to u minus 1 will be what? 256, exactly. 256 is less than 60, less than equal to 512. This condition satisfied. If this condition is satisfied, you will allocate entire block. That is the approach. Otherwise, what you need to do? Split. Just like what we do in tree or in a binary tree, right? You divide the current available block into 2 parts. For example, if your request is u is in multiples of, you can say 2, as I said, we'll see that, right? We'll see in the example, Priya, in detail. Yes. Otherwise, block is split into 2 equal buddies. The example is 210 bytes, if that is the request. Is this condition going to be satisfied? The condition is 256 less than 210 less than or equal to 512. Condition is false. So what you will do? Split the current available space. What is current available space? Yes, 512, isn't it? That is your 2 raised to u, right? 2 raised to 9, in other words. Okay. So 512 will be split into 2 equal buddies. So now we will have 2 blocks of which size? 256 and 256 each, exactly, right? Check the condition again. Is it satisfying now? What will be 2 raised to u minus 1 in the new situation? 128. 128 less than 210 less than equal to 256. Following this, yes or no? 128 less than 256, sorry, 210 less than 256. Allocate that. Okay. So this is the approach. So we continue until what? What is the stopping criteria? Smallest block greater than or equal to S is generated. Clear with the approach and the algorithm? I'm going to give you a complete example. Don't worry. Right? We have a very easy example coming up. Okay. Let us take some small examples. Then I'll go with the actual example. Okay. As I told you, suppose block is of 512. Request is 512 again. Can we satisfy? Obviously, yes. Right? So allocate the entire block. Okay. Request 400. So again, we check U minus 1. Right? Less than 400, less than U, that is 512. Again satisfied, go for it, right? Request is 200, condition is false, right? So split, and then check the condition once again, okay? And allocate the 256 byte block. So yes, there is fragmentation over here. Which kind of fragmentation? We are allocating 256 byte block for 128. Which kind of fragmentation is occurring? It is internal, right? But still, this is a tree-based approach, right? So that is why the searching time will be less, as well as we are using simple splitting as the approach, right? So that is why it was found efficient when this approach was, you can say, announced. Fine. Let us take a complete example. Suppose available space is 1M, that is 2 raised to 1024 bytes, right? Idea behind the condition. Idea behind the condition is very simple. You keep on dividing until you get the equal size, right? Or at least you get the nearest size, right? And the criteria should be dividing into equal bodies only, right? That is going to be very simple in nature. That is why, right? And you can use the tree method as well. That is another reason. Okay. Fine. I'll go with the example now. Request is of 100K. Now, how many times you will have to split? If request is of 100K, first 1 MB has to be split into 512 and 512. Okay. Then 512 will have to be split into 256, 256. Okay. Still, is the condition going to be satisfied? That is correct, 3 times, right? One more splitting. 256 will be further divided into 128, 128. And we allocate the left-hand side block. Generally, we start scanning from left to right, right? You can remember this rule for solving the buddy system examples. Start scanning your memory from left to right. So you are allocating the first block over here, right? Okay. The rule of buddy system says that if you have split particular memory, if you have split a particular memory, then at least one of the buddy has to be allocated. At least one of the buddy has to be allocated. That means, who is the buddy of this 128? This is free, right? This is free. Who is the buddy of this? This one? Yes, A. So the rule says that when you have allocated the memory, right, one of the buddy should be allocated. Otherwise, you should not do the split. That means, otherwise, this block should be entirely of 256K. Obviously, right? Isn't it? We will see this later on when we go with the example, right? So it will be clear. Okay. Fine. Next is 240. Now tell me, it is very easy. You start scanning from left to right. You will allocate this over here. Yes or no? You already have this block, available block, right? So it's very easy for allocation. Next, 64K. Now you check the available list, right? Which is the nearest size block we are having? 128. Now, is the condition going to be satisfied for this 128K? 2 rows to U minus 1. That is, what is the request type? Yes, we have to divide that 128K into 2 blocks. right, as per the condition. So I'll divide that into 2 blocks and C is allocated over here. Are you clear up to this? It's very easy to solve this buddy system example, right? Much easier than what algorithms you have seen earlier, right? Okay. Next, 256K. Again, very simple decision. You have the 2512K block available that can be split and you go with this 256, right? Okay. Let us continue. Now, the next operation is release B, right? In exam, you might be given this kind of request array, right? Suppose you are given A of 50K, B of 100K, C of, let us say, 500K. And then the next line is saying that release A, right? So at the time of release, you need to take care, right? We'll see what care we need to take. When you release B, right? What block B was occupying? 256, right? But when you are releasing the block, you check for the body. Is the body also free in this case? Who is the body of 256? This 256 block. Yes or no? Right? In general, I can say this 256 block. Okay. Is it free? It is not free, right? If the body is not free, then you only free the current block. Current block is this, right? But what if the body was also free? We will encounter this situation later. Yes. What if the body is also free? You have to merge, right? Don't forget to do this when you are solving the example, right? Always keep checking for the, and this is why this system is known as a buddy system, right? Always keep checking your buddies, right? Okay, let us continue. After release B, the next request is release A because its job is done. So we are releasing the memory space of A, right? So what will happen over here? 128K will be freed. Are we going to merge that? No, right? What is the reason? Body of this 128 is this. It is still occupied, right? So you don't merge, okay? As simple as that. Request 75K. Where we can accommodate that? We had 3 options, 128K, 256K, and 256K, right? But we start from left to right. So we go with this 128. That's correct, right? Next request you are given in the exam is release C, right? Where is C allocated? Over here, right? Is the body free? Yes, body is free in this case, right? So merge and make a large block. Okay. So are you getting? We are following a tree, right? Actually, if you try to map this concept on a tree, it becomes easy for allocation and deallocation. And that is why this is a faster approach, right? Okay, release E. Now see what happens. When I release E, the body is free, right? So if you just make a 256K block, it will be incorrect. Why? Because the next body, that is this 256, is also free. Okay, so finally what you will get? A 512K block. Following up to this, yes, I'll repeat. See, we wanted to free this, right? 128. Okay, we check the body. Is the body free? The answer is yes, right? So we merge this 128 with this 128. But we should not stop over here. We have to continue. Yes, okay, Urjit, fine. So now we are done with this part of freeing approach, right? If you take it further, release of D, what will happen over here? 256 will be merged with 256, you will get 512. 512 with 512, you will get entire memory free, right? Same approach, okay? You solve this kind of example given in the exam, right? You need to find out just allocation, right? And be precise while you are allocating, okay? Always follow left to right approach, as I said, fine? You will find many examples in the exercise of our textbook, as well as many online examples, right? Buddy system is a very popular memory management technique. The reason for that is what? It is using tree. And tree traversals, as you know, are very efficient, right? So If I represent one snapshot in a tree, it looks like this. Just observe this part, right? This is representing which scenario? Where A, C, and D are allocated. This one, right? A, C, and D are allocated, right? So just look at this. A is allocated with 128, right? C is allocated over here, right? And D is allocated over here. Now check for that condition. Wherever there is a leaf node, the body is allocated. Yes or no? If you check for this body and this body, right? One of them is allocated. Can I say? Right? If you look at over here, this one and this one, at least one of them is allocated. Although it is not the leaf level, but still we can compare, right? If you take an example of this one and this one, at least one of them is allocated, right? If the second one is not allocated, what we need to do? If the second one is not allocated, merging is required, right? So that is why this is a very popular approach used by some of the operating systems. I would not say all, but some of the OSs which are less complex, right, are using this approach till date, right? Okay, so the rule of merging, as I said, it is written over here. If two bodies are leaf nodes, then one of them must be allocated, right? Otherwise, they should be merged. It is a very simple rule you need to remember, right? At any point of time, leaf nodes define the current allocation. Agreed? Because if you look at this diagram, right? This is a leaf, right? And this is a leaf. If you sum it up, what you will get? Total allocation. Yes? So that is the simplest approach. Okay? What is the negative side of buddy system? I have not kept that in slide, but we can discuss that before we end. What is the issue you find over here with buddy system? Yes? There is some amount of internal fragmentation. What if a large block has to be allocated but space is not there? Yes, it won't be accommodated, Janil. I got your point, right? It won't be possible. Split and merge operation are costly again, you can say, right? Height of tree, if it is high, it can be complex, agreed, right? So that is why I said it can be used in case of simple operating systems where you are not having too many processes, right? If you are having too many processes, this method might not work, right? Yes, exactly. It is not for complex OS like we have nowadays. In current scenario, paging is the solution, or the version can also combine paging with segmentation because that gives both the advantages, right? Earlier, some OS were relying only on paging, but then they realized that if I combine paging with segmentation, I'm going to combine both the advantages, right? So but which one Unix is using? Yes. So that depends upon the Unix version, Preet, right? So you can explore that, right? Because every system is using a different methodology, right? Yes. Okay. Next is relocation. Before we end, I'll just take 1 more minute, right, to refresh this because relocation is required for tomorrow's lecture, right? So that's why I'll just refresh. Relocation is what? Shifting the process from one location to the other, right? And as you know, location of a process is not fixed, right? It can change over the period of time. Agreed? We have seen many examples, right? What are the reasons for relocation is required? The first reason is swapping. Because when you swap out a process and when you bring that inside, are you going to get the same allocation, same area where you were allocated earlier? Very less likely, right? Another frequent reason is compaction. If you are using dynamic partitioning, compaction is frequently required. And as many times you do compaction, those many times what we need to do? Relocation. It is having direct implication, right? So Now, before we go into paging, we will discuss the concept of logical addresses, physical addresses tomorrow, and then we'll start with paging. So tomorrow's class is important because we are going to start with an important topic, paging. That is going to be used throughout for the remaining lectures, right? Okay, so thank you. Let us end this session over here. We'll continue tomorrow. Now AKG sir will take over, right?